Okay, with sound. So I can draw the diagram that corresponds to the set of perceptrons that we have here. Those would be the two input nodes. It's a 2D feature space. So we have these input nodes, x1 and x2. And then comes the so-called hidden layer of 4 perceptrons. And I should have made these bigger such that I could have drawn the summation sign in each of these. Sorry. So this would be the summation unit. And then each summation unit corresponds to one perceptron, so I need to specify its parameters. Those are the parameters of the normal vector plus some bias that tells me how far from the origin does this perceptron lie. Okay, then each of these, each of the outputs of the summation units goes into an activation unit or activation function. And in this particular case, I've used the crisp activation function again to say that up to a given value I get 0, and then all of a sudden I get 1. Okay, so I've used the step function here. And now what do we do with the output? I can draw a different picture to show the same or to try and illustrate the same geometry here. It's a bit difficult to draw a 4D hypercube, but I will try. Really? So let's take white for the outer part. And let's take yellow for the inner part of this hypercube. Okay, more or less. And now to make things more clear, I will annotate all of the edges. So let's say that this upper edge here would be the corner 1, 1, 1, 1. And now take any order you like. And so on. And now the inner part of this hypercube has the same numbers, except that I will always have a 0 in the first position. So this edge here would be 0, 1, 1, 1. And this edge would be 0, 0, 1, 1, etc. And I need a couple more edges because the outer hyper or the okay, I've seen nicer pictures, but I think you get the idea. So it's two nested cubes, and the outer part corresponds to one surface of this hypercube or to one set of nodes, the inner part to another set of nodes. Okay. And now, in this sketch of 4D space, I could now put in, let's say, a single additional perceptron. So a single additional perceptron in this picture here means I put in just one more summation unit with its activation function. And this now has 4 inputs plus the bias. And out comes a single class prediction. So this single perceptron, let's see what set of corners it could cut off. And one set of corners that it could cut off would be this one here. So these 3 corners versus all the rest. And if we look at these 3 corners, so it's 1011, 1101, and 1001, it would correspond to this area here. So you see the overall decision boundary that we would get would be this one here. And, well, that is something, that is a shape that we could not produce with, for instance, quadratic discriminant analysis. So you see that this gives us more modeling power. We can generate more flexible decision surfaces. So we have a correspondence between the corner of a hypercube, or the corner of the hypercube that corresponds to a single one of, so one corner of our hypercube corresponds to a single one of these polyhedra that are defined by this set of perceptrons. And this would be our intermediate feature space. And if I now introduce a single output perceptron here, I can create any decision boundary which can be obtained, well, in this intermediate feature space, so by cutting off some corners of this hypercube. So in other words, all those unions of polyhedra whose hypercube corners can be cut off from the rest of the hypercube by a single plane. So all those unions of polyhedra, they can equivalently be represented as a two-layer perceptron with a single output node. So using this geometry here, or this architecture here, we cannot create arbitrary decision surfaces. For example, let's take as an extreme example, you know, this these opposite polyhedra here. So let's say the region 0, 0, 0, 0. And the region 1, 1, 1, 1. These lie on opposite sides of the cube. And if you think even of a rectangle, you cannot cut off the two opposite sides with a single decision surface. So in that case, we need a more flexible architecture. We could cut, or do you have an idea how we could cut off these two polyhedra, or these two corners of the hypercube?
In our first example, we cut off the two different corners of the square, so maybe with just another perception.
Yeah, exactly. Exactly. So we add another perceptron, and let's say we take this perceptron to cut off only this corner of the cube, so only the 0, 0, 0, 0 corner, and we take that perceptron to cut off only the other part, the 1, 1, 1, 1 corner, and then, and I'm running out of space, then we would need just, you know, an additional perceptron, an OR perceptron that checks if either one or the other is activated. try and squeeze it in here. So another summation unit. Okay, but at this stage we now have a 3-layer network, so a network with 2 hidden layers. And that is a general statement, so that with such a network with 2 hidden layers, you can really approximate just about everything. So, in fact, one can show that even 2-layer perceptrons with just a single hidden layer, that they are so-called universal approximators. So if you just use enough perceptrons here in the first stage, you will be able to approximate any function you like. But in fact, the argument that you've just given, it's a deep argument. So you can, because this is constructive proof, that with a 3-layer perceptron with 2 hidden layers, you can approximate anything you like. So let's have that as a separate point. So 3-layer perceptrons with 2 hidden layers. They are also universal approximators. I have not written down that in fact already 2-layer perceptrons are already universal approximators, but that's harder to show. So universal approximators, and the constructive proof goes as follows. First you will partition feature space in such a fine-grained fashion such that all polyhedra are pure. So that in the classification setting which we're discussing here, such that you will only have representatives of one class in any given polyhedron. So if 4 are not enough, you can use 500. And then secondly, you will add another hidden layer where you create a second hidden layer where each perceptron cuts off a single corner of the hypercube. Namely, all those single corners in which representatives of, let's say, the class number 2 can be found. And then finally, you add a single OR perceptron as in your final layer, as your third layer. So an OR perceptron means that if at least one of its inputs is activated, then the output is also going to be activated. So this would be a perceptron where all the inputs are 1 and you have no bias, and you then put this through your activation function. Okay. So what has happened overall? We have mapped a problem that was not linearly separable we have mapped it in a nonlinear fashion to some higher dimensional space in which it did become separable. And this is something also known as the projection trick. Okay, I think you're entitled to some questions. So I think this is really the most important part of today's lecture. This notion of taking a problem which cannot be solved with a linear method in the original space, map it non-linearly to a higher dimensional space, and then treat it with a linear method in that higher dimensional space. Any questions?
So this constructive proof, you need as many perceptrons as you have these partitions, these pure positions?
So the question was, in this constructive proof, how many perceptrons do we need? So the number of partitions that you create from the number of perceptrons, it really depends on their relative arrangement. And here, for example, we have not realized all possible partitions that you would expect naively. So we have 4, so this hypercube has 16 corners, but here we have less than 16 partitions, because some of these, well, cannot be mapped anywhere. So, for instance, the partition which, let's say, lies simultaneously.
Actually, it's on the top, 1, 0, and 0 is wrong, and it's not possible. No.
This one is wrong.
Yeah, because 2 is...
So it's above 1. It is above 2. It is above 3, and it is below 4. So this is 1, 1, 1, 0. And the number that I had originally written there, thank you for the correction, the number I had originally written there is one of these regions that we do not find anywhere. So in general, if you have, some complicated, take a new picture, if we have, let's say we want to approximate this decision boundary here, where we say inside is class 1 and outside is class 2. You could now take many perceptrons to approximate this boundary, and then take all these polyhedra that correspond to the inside as belong to that one class. And how many perceptrons you need, really depends on how complicated your decision boundary is and how closely you want to approximate it. And well, that is now in practical terms, that is the real big problem in neural networks, to decide how many perceptrons do I need firstly, and then secondly, how do I position them appropriately in space. I have so one crucial choice is really the architecture itself, how many perceptrons in each layer, but then there's also the question of the activation function. So here I pretended that as we go from one side of the boundary to the other, my output jumps from 0 to 1, and this is true for a step function. But in reality, you can imagine using much smoother functions. So, to have something sigmoidal that along this fourth dimension here, we have low values, then we have intermediate values, and then we have high values. And this has two consequences. On the one hand, it rounds the corners of these decision surfaces. So as soon as I don't have these harsh transitions anymore, I will get softer corners here. But it also makes the numerics much better behaved, because if I use this harsh activation function, my error or my penalty will jump whenever my decision boundary traverses one of the misclassified points. And if I have a smoother activation function, I will be able to propagate or to have a much smoother energy hypersurface. Okay, you can imagine that associated with this problem is an energy hypersurface. It has as many dimensions as my neural network has parameters, and I want to find the global minimum of this energy function. And if I use these sharp activation functions, my energy surface is locally constant, and then has all these staircasing artifacts, and that makes for a difficult minimization problem. If you use a smoother activation function, it makes for an overall much smoother optimization problem.
But then finally you need one step function if you want a decision between two classes.
In the very end.
Want to destroy again all the smooth functions in the intermediate layers? Because then the loss function that you define is again jumping, because you have either class 0 or class 1.
Yeah. So the question is about the very last activation function. If it doesn't have to be crisp, you can take a smooth sigmoid, or that's what you usually do. So you take relatively smooth sigmoids everywhere in your network until you have converged to a minimum, and then you crispify your output. So then at the very end, you turn your final activation function into something sharper. But remember that often you're not only interested in getting a classification for a point, but also in a confidence. And the most primitive confidence measure you can have is to look not just at a predicted classification, but to look at a predicted posterior probability. So in that sense, you do not only want to know is your final output above or below 1/2, but you would like to know, okay, was it 0.55 or was it 0.999, which will give you a bit more confidence in your result. Okay, and then around the choice of these activation functions, this is a whole business. So you can either treat them as free parameters, so the steepness of your sigmoid function, you can treat that as a free parameter and learn it, or you can have a kind of annealing schedule where you start with all of your sigmoids being very soft to bring your optimization problem into the general vicinity of a good minimum, and then making all activations functions crisper and crisper over time. But in essence, it is a very high-dimensional global optimization problem with multiple local minima, and really for all but the smallest architectures, there is no hope of definitely finding the global optimum. And then people come up with lots of engineering suggestions on how to optimize this well. And they make a big difference in practice. But it all really only shows that from the practical standpoint, the problem is not so well posed. And this is exactly why they're not used so much nowadays. However, the reason I'm still talking about them is that I think they clarify this particular ansatz that other methods use implicitly, or more implicitly than neural networks do. Okay, so why does mapping to a higher dimensional space help? And this is the subject of the function counting theorem, which had been proven by many people, but the proof that people look at nowadays, and which is much simpler than the original ones, is by Thomas Cover. You may know him from this fine book on information theory, and I like his thesis, so you can download it on the web, and it has 70 pages, rather sparsely typed, but it's very, very clear. So you can, it reads extremely well, and he has produced a simple proof that I will show you in a minute. Now, he is looking at the function counting theorem. The function counting theorem is looking at the number of linearly separable dichotomies or groupings as a function both of the number of points and the dimensionality. So let's consider 4 points which are arranged in these positions here. So I have a total of 8 possible ways of assigning classes. So I could say that this is all of them are class 1, or I could say all of them are 1, but one is class 2. And so on. And well, this one is linearly separable, trivially. Okay, this one is linearly separable. This one is linearly separable, and this one is the XOR problem, is not linearly separable. And the function counting theorem looks at the number of linearly separable dichotomies, so at the number of ways of assigning class labels to points whose coordinates are given as a function both of number of points and the dimensionality. And the result looks like that, and we will study the proof in a minute. So this plot takes a moment to understand. On the x-axis, we have the number of points divided by the dimensionality plus 1. And on the y-axis, we have the fraction of linearly separable dichotomies versus all possible dichotomies. And these curves that I've plotted are for different dimensionalities. And the higher the dimensionality, the closer this curve approximates a step function. And what you see in essence is that as long as you have no more than twice as many points as dimensionality, you are able to separate all possible linear dichotomies with just a linear classifier. And if you have a little bit more, then you are only going to be able to separate a tiny fraction of all those dichotomies. So to make things concretely, let's say you have 199 dimensions, and if you have, let's say, 390 observations, then you can now assign class 1 or class 2 in all these possible ways to your 390 observations, and almost all of these assignments are going to be linearly separable with a decision surface. So you will be somewhere up here. And if you now move from 390 to 410 observations, then you are suddenly, so the absolute number of dichotomies grows, because 410, 2 to the power of 410 is more than 2 to the power of 390. But the fraction of linearly separable ones will be exceedingly low. Okay? So if I want to have a linearly separable problem, I should either have very, very few points, or I should have a high dimensionality of these points. And if you now look at multi-layer neural networks, in essence, this is all about artificially increasing the dimensionality of your points. Okay, and I rarely show any proofs in this class, but this one I will show, because I think it's a deep result. So it's not something I would want to have to do as homework. So to prove it, and it's still relatively, once you've seen how it works, it's relatively simple. But it has taken a while to find a simple proof. So people had known that proof for a long time, until 1963, young Thomas Cover came along and made it all much, much simpler. Okay, so the function counting theorem, we work in homogeneous coordinates. So meaning that our linear classifier can just be written So classifier can simply be written as W transpose X without having an extra bias term here. And we also assume that the data or the observations that they lie in general position. Meaning that we have no artificial linear dependencies in there. So as an aside, we say that a set of n vectors is in general position in p-dimensional Euclidean space. If every p-element subset of our data is linearly independent. So in practice, this means if I plot my observations, I prohibit that any three of these should lie on a straight line, for instance. So if that was the case, then they would not lie in general position. So it just means you don't want degeneracy in your data. Okay, and the question now is, how many, so assuming that we work on homogeneous coordinates and assuming that our observations lie in general position, how many linearly separable dichotomies are there? And the answer is by an induction argument. So assume first that we have a number C of n and p linearly separable dichotomies. So this number means of n points in p dimensions. And we now add an extra point which we also assume will lie in a general position with respect to all others. We now want to know how, adding this extra observation, how many linearly separable dichotomies will we have then? And the answer is that we, on the one hand, we keep all the linearly separable dichotomies that we have before, so then we anyway still have C n p, and the explanation is from before, with the label of our new observation n plus 1 suitably chosen. So let's say we had a separation between the points, between these 3 points. This is wrong, sorry, because I want to separate the 1s from the 2s. And I could now simply assign class number 2 to this additional point because it lies on that side of the decision boundary. So if I pick the label just by according to what side of the dichotomy it lies on, then I just keep the number of linearly separable dichotomies that I had anyway before adding this point. So in this case, I would infer that this point should also be of coordinate 2. But now what if I insist that this point should be of class 1? Will it then still be possible to to separate the points. And well, we see that actually yes, but how can you argue that in general? And the argument goes as follows. It comes from the realization that I can only assign both possible labels, 1 or 2, if I can find a dichotomy of the remaining points that goes right through this one. So I'm adding the origin. Let's say this is the origin, and this is my point xn plus 1. And if my decision surface goes right through this point, then I can wiggle it a little bit. I can move it up a little bit or down a little bit, and I can correspondingly assign the label 1 or 2. This freedom I only have if it really lies exactly on the decision surface. Now, the decision surface is characterized by its normal vectors, and we always work in homogeneous coordinates. So, in other words, it lies, or it can lie on the decision surface only if this condition w times xn plus 1 equals 0 is fulfilled. So only if they are orthogonal, if these vectors are orthogonal to each other. And these vectors being orthogonal to each other means that I can only look for separations in the orthogonal subspace. So in the subspace with one less dimension, which is orthogonal to xn plus 1. So additional linearly separable dichotomies can only be realized if the new point xn plus 1 lies on the decision surface and that in turn means we can optimize the decision surface, or we have to search for linearly separable dichotomies only in the subspace that is orthogonal to this vector xn plus 1. So this will give us overall a recurrence relation if we, this is our extra point that we have added, and we have recovered all those linearly separable dichotomies that we already had before by just assigning the appropriate label to this extra observation, plus we have in addition all those linearly separable dichotomies that can be realized in the subspace that is orthogonal to this new observation. And this subspace has one less dimension, so p minus 1. Okay, now comes all the machinery of recursion. So this first term could be rewritten as c of n minus 1p plus c of n minus 1p minus 1. So this is inserting the recurrence for the first term. And then we get for the second term and so we have this term once, this term is identical, we have it twice, and this term we have once. And you can now insert this recurrence again and again, and you will get out a Pascal triangle of the number of the frequencies with which these terms appear, meaning that these will be the binomial factors. So these are the binomial coefficients. And the last thing I have to specify is the termination condition. So I'm sorry, there was not enough space down there. So with the following termination condition, with one point in one or more dimensions affords two linearly separable dichotomies. So the one point can either be of the one class or of the other class. And if we have one point in 0 dimensions, so just a single point in no space, we say that it affords no dichotomies at all. And then overall, this gives twice the sum over those binomial coefficients. Okay, and this is the subject of the theorem, of the function counting theorem. There are C, N, P in homogeneous coordinates, so homogeneously, linearly separable dichotomies of n points in p dimensions. So note an important technical point, namely that the points had to be in general position. So if I just took, let's say, if I just took some matrix X of observations, which is P by N, and if I then projected to a higher dimensional space, as we had seen in probabilistic PCA, with some matrix, let's say d by n, or sorry, d by p, with d larger than p. This would be a linear projection to a higher dimensional space. And as a consequence, the points would not end up in general position, and hence this function counting theorem would not hold. So it's really crucial that this mapping be of a nonlinear nature. Okay? Otherwise, well, you just map your points to a subspace that is embedded in a higher dimensional space, but it makes no change to the geometry. And this is something that you will see again and again in pattern recognition. There's really this nonlinearity that is crucial. Now, this idea of mapping points to a higher dimensional space is exploited by many methods. For example, here in polynomial regression. So I have a couple of points here. So this is y as a function of x. And you see that a linear fit to these points would be of poor quality. However, I can perfectly fit a parabola to these points because it's actually how I generated those points. Now, if I map my original observations x to a higher dimensional space spanned by x and x squared, this is what you see here. So these are the original observations, and I've shown their position above the plane by this stem plot. I can now fit these points with a plane. So this parabolic fit here, I can rewrite it as, or I can say that y hat equals alpha times x plus beta times x squared plus some gamma. You see that it is linear in alpha, beta, and gamma. And this is just the example that you see here. So in polynomial regression also, you explicitly map to a higher dimensional space in which your problem becomes linear. I have another example here. Again, the XOR problem. We have points of class 1 and points of class 2. And in this case, so the original feature space was just x and y. And I can now augment this feature space by a third dimension, x times y. And this is where the points end up. And now by a decision surface like that, I could now separate these two classes. And in particular, in support vector machines, which we will discuss next time, this is also what's happening, that points are mapped to higher dimensional space, except that with support vector machines, the trick is that this mapping is only performed implicitly and not explicitly. Okay, so this is the take-home message of today, that non-linearly, you see the non-linearity here in this third dimension which has been added, or you see the non-linearity here which has been added in augmenting the space. Non-linearly projecting your data to high dimensional space may make the problem amenable to a linear solution. Now this all sounds very wonderful. Of course, the downside is that it also becomes much easier to overfit in these high dimensions, because I could now reverse the argument and say that if your points are in a sufficiently high dimensionality, I can always find a linear hyperplane that will separate the two classes, no matter what amount of the positions of your points can be explained by noise, and what part really is something that you want to learn. Okay, do you have any questions?
So this nonlinear function is chosen arbitrarily?
So the question about the nonlinear function, in this example, I have wisely chosen it to be exactly the right one. The choice of the nonlinearity is crucial. So in support vector machines, you will have a kernel that embodies this nonlinearity, and both which kernel you choose and then the parameters in the kernel really determine what your result will look like. Or going back to these neural networks here, I mentioned briefly that so if I made all these activation functions perfectly linear, then I could only fit a linear decision surface, or just I could just fit a linear function in this plane. On the other hand, taking these sharp step functions will give me these binary transitions between polyhedra. And somewhere in between, so what people really do is they look at families of activation functions where in the extreme case you have a step function, in the other extreme you have a very shallow sigmoid function, and in between are those parameters that you will really work with. So if you make it totally linear, this makes your optimization problem trivial, but it also takes away the modeling power of your method. If you use the step functions, you can have very sharp transitions, but it's extremely hard to optimize. And in practice, people will operate somewhere between these two regimes, so to give you somewhat rounded decision surfaces. And as I said, you can either try and learn these activation functions in the fitting process, or you can just impose them by starting with very linear functions and then making them more and more nonlinear over time. Any more questions? No? Okay, break.